Hello community, so great that you are back. Today we talk about new solutions in AI. Today at breakfast it happened, August 12, 2025, I read here an email by Gary Marcus and he had a beautiful example here. There was, hey, GPT-5 recommended here a new place, very cheap, beautiful. I followed the link and it turned out the article quoting here those prices was a 10-year-old article. And the question was, why does AI do this? Why does GPT-5 do this? Why doesn't it understand that an article 10 years ago does not contain the information that I need, especially if it's about price? And the answer by Gary was simple, no? Because GPT-5 does not have functional models of the world about timing, pricing, economics. That's not how they are built. And they never managed to properly learn such models. So if you think about this would mean we have a complete disconnect of an extreme body of knowledge of all of Wikipedia without an understanding how the world is connected. I love this world model idea, so let's play with this a little bit. Let's discover first the latest research about AI world models. And this will lead us to another topic of emergent communication. You know, in my last videos, I talked about here why GPT-5 fails with complex tasks, and I gave you this simple explanation in my video. But today I want to find a solution to this problem. And let's be frank, is world model implementation a solution? How we can fix GPT-5 or the next GPT-6. But you know, I don't want here a brute force methodology like NVIDIA, where they manage to build world models with, I don't know, 1,000 NVIDIA GPUs, 10,000, I don't know. Because if you look here, just yesterday, NVIDIA published here, following the hype of GPT-5, no? They have now complete new models here they call Cosmos, no? They are now physical AI models that understand everything, no? It breaks through the world understanding, no? We have now robot and vision AI agents, they reason like humans. And I thought, oh my goodness. But you know all about these World Foundation models, because 4 months ago I had this video, I showed you the insights by Harvard, DeepMind, MIT, IBM. What is the technical background, how we code this, what is here the essence of those world models and why NVIDIA needs it for their robotic system. But let's forget about NVIDIA for a moment. Let's focus on the main idea that we encountered here, a world model. So let's start at the beginning. When did a world model emerge first? Now, it might be Mesopotamia, but let's go with Old Egypt about 3500 BCE, né? And here you have a descriptive world model, as you see, the mighty sun god Ra, depicted here with a head of a falcon crowned by a vast glowing sun disk encircled by the, yes, you know, great, on the journey across the heaven. What was the use of this world model? To explain to the old Egyptian why the sun rises in the east, travels across the sky and sets here in the west. And why this is happening every day. And they needed here a world model to understand nature. And they developed this descriptive world model. Now, about 5,000 years later, we had Nicolaus Copernicus here. And he changed this world model. He developed here, if you want, a more geometric world model, no? With the sun in the center, and you get the idea. Now, of course, today we have a pure mathematical world model, abstract, about graviton, string theory, Higgs boson theory, cold universe, and whatever. But now today in this video, we have not a task. Hey, how do we explain a world model to AI? And how does a Gemini, a GPT-5, or the upcoming Sonnet 4.5 system builds and understand their own world models within the AI complexity? And how does this world model suddenly empowers an AI system like GPT-5 or GPT-6 to solve here the problems that we found in my last video? So we have here our little robot looking for a solution regarding complexities. a brand new paper. Here we have it, August 8, 2025. This is the archived link. And here we have Fordham University, City University of Hong Kong, and IBM Research talking about a new framework they call Coral for communicative world models. So this is now interesting. I don't need here the complexity of NVIDIA clusters. Can we build this with 2 agents? Is this possible? Let's have a closer look at this study. Now this Coral framework, the design is centered here on a simple insight that we need an asymmetric learning objective, and in the simplest case we go with 2 agents. And then we have an, if you want, control agent that does action in this room, and we have an information agent that built here a mental model of the environmental dynamics of all the elements in the room. Now we need a communication protocol between those 2 AI agents because, they should know about the existence of the other one and they should use the abilities of the other one. Now, interesting, if you have an asymmetric learning task, what we have, you have, if you want, an information agent communication that must now be explicitly shaped to benefit, to be useful for the control agent, for the active agent control policy optimization that we know from reinforcement learning. And it doesn't matter if we go with in-context reinforcement learning or we stay with the classical reinforcement learning. This is about a deeper understanding and a new framework here. Now, in my last video, I showed you it's easy to disassemble here complex system or decompose here a high knowledge perplexity system with a high complexity sheet. So the first idea is, let's build a world model. Let's have an agent here, the IA agent. So they have data, a LiDAR scan data. It scans the environment in the room, in the world. Or we have video frames, all the video recordings of this particular room, of the dynamics of all the objects in these rooms. And then we have, if you go physics simulation, whatever data you have, you encode those data. And the job of the first agent is build a world model, build a coherent understanding of all the interaction in this particular room. Or if you really go like NVIDIA with, I don't know how many thousand GPUs, build a world model. Let's say for an autonomous car. You get the idea. Now we could talk about the complexity of a decomposition of a world model itself, but let's make it easy. Let's talk about the decomposition of a single complex problem at first. And this is now where I want to show you here this new framework that's called Coral. It asks itself, hey, how does an agent learn to act intelligently and adaptively in a wide variation of situations? Because let's say our control agent does not know if you move around some of the object in the room, how to solve it now, because it was trained on a different object configuration. Now this is where the second agent that has a world model comes into play. And now the second agent, the information agent, explains, if you want, the new situation to our little active agent, if you want, the control agent. And there are so many layers in this publication, and I hardly missed this paper because, you have to read this paper, but read it from different perspectives. You will be amazed. So Coral decomposes here, if you want, this monolithic challenge into 2 conceptual, simpler subproblems, no? In 2 agents. So the first is, if you want here, the physicist that says, okay, what are the rules of the universe? What are the rules of the dynamic in this room? And a system says, hey, forget about rewards, forget about goals. I just observe here this world, this room, and I learn to predict what will happen next. I sit there for weeks and months and years and I record everything. I have a complete understanding of the temporal dynamics, how objects interact, everything. Cause and effect, I can deduct here everything, all consequences of all action I observed. And I can tell you what will happen in the future. I can predict here the effect. This is the information agent. Objective is to minimize its world prediction error, the loss function here. And the second is, of course, we have to have an active player in this room. No? This is our control agent. Now we train the control agent. The objective is to maximize here the task reward. And you know what? You can go with the simplest PPO objective. You don't need GRPO or whatever. Just go with the simplest there is. Because it is not about a singular learning experience, about a singular reinforcement learning or a singular reward function. We have now a complex system dynamics that we have to train. Now take a step back and think about this. This new Causal framework conceptualizes here the learning problem of multi-agents through a functional separation of the representation and the control of the world. So we have a dedicated, you see, we decompose a complex problem. So we have a dedicated information agent that learns here the dynamic model, while another decomposed system, lower complexity, a control agent, is tasked here with maximizing the rewards for particular tasks. And this structure allows here the information agent a learned protocol to serve here as a powerful contextual prior for the active agent. And therefore we have an in-context adaptation of this knowledge. So we have here, if you want, the information agent that can foresee the future, that is the future dynamic of the room. Let's stay with this environment. And it can foresee also the action that a control agent might take. And it feeds this knowledge to the control agent, so the control agent does not start from zero, from scratch. It can, if you want, select from a higher complexity representation and choose its specific agents. Yeah, contextual prior, short explanation of what is a contextual prior, how the world works, provided continuously by the pre-trained expert information agent. And then this knowledge is, if you want, contextual, because for a particular job of the control agent, it is exactly the message that it needs at every single time step. Yes, we're in a loop, a continuous learning loop. And this is necessary and important for the current context of the game and the training where the, if you want, CA agent is acting. Yeah, in context adaptation, I think it's clear. But let's look at the flow. So what we do, we separate the job, again, a decomposition of complexity of understanding the world from acting in the world, because our AI systems like GPT-5 cannot handle this complexity. They fail at this. So we says, okay, little LLM, your job is this, and another LLM, your job is that. And then we have multiple LLMs, and everybody gets a little simple job. So let's assign here the understanding job of the world model here to the information agent, and let's assign here the acting job to the control agent in the simplest scenarios we can think of. No? So we have here just a reward-based optimization problem, and here we have a complete different complexity. And in the end, what we have, a pre-trained communication expert who acts as a powerful source of prior knowledge for the new control agent, allowing this control agent to adapt and learn new tasks incredibly quickly, because it provided for every second, if you want, a task-specific action prediction of the environmental dynamics. But did you notice that we missed here one piece? And it is that we have to train them together. Why? Because the information agent has not just the task of watch everything, analyze everything, build a temporal dynamic model of this environment, of this room, but it has an additional complexity. It has to learn to communicate its understanding, its prediction to another agent effectively. So we develop now a communication protocol between two agents, and guess what? It will not be the human language. Do you see how many layers we have to this beautiful Carl framework? If you just take a step back. So now let's not talk about the difficulty of reassembly a complexity system. No? And this is where most systems like GPT fail. I showed you in my last video. And now if you have two separate systems in isolation, we encounter problems. Let's understand why it's not working. Imagine you train here your theoretical physicist AI in a lab. It learns everything about this particular world, this particular room. It develops here a perfect but highly technical internal language to describe it. And it read all the textbook on theoretical physics, everything on mathematics, everything on logic, and you got it. And then you bring in your robot. And the robot enters the room. But the robot has been trained also in a simulated environment, but it has been trained separately from the first agent. And now you put those agents that has been trained separately in a room together and ask them to cooperate. So guess what's gonna happen? The physicist AI agent, the information agent who built a complex equation world model with state vectors and whatever, starts now to describe here the future temporal dynamics of this environment to its companion, the control agent. But the control agent has only been trained. You're in a room. If your task is take the milk out of the refrigerator, the control agent goes to the refrigerator, opens the door of the refrigerator, takes the milk bottle out, and this is it. No theoretical physics at all. So guess what? They do not share a common language. They do not share a communication protocol. And the reassembling fails because the information from one piece of agentic system cannot be integrated into a coherent, high complexity knowledge for the whole system. So the interface between them is broken. And now the authors of this paper had a beautiful solution. They were here really forging a shared language. And I really mean this metaphorically. Have a lot of effort. Create something strong and lasting with a considerable effort. Yeah, it's a pre-training. You say, oh my goodness. So this idea is not just in performing here the decomposition of the complexity and the separation here of multiple agents, but it is here in this sophisticated method I'm going to show you in a minute. So it's not just stick here two pre-trained agents together. No, they forge here really a new link between them during the pre-training process of our two agents. Now again, if we pre-train them in isolation, we have a problem. So we pre-train them here together, interacting in the same environment, in the same world. And both agents know right from the beginning, they are not in isolation. They have a big brother that is also tasked with particular jobs to perform. So they co-evolve now. So this means if you train an LLM that is the brain of an agent, and you always use GPT-5 here for this task of your multi-agent system, it will fail. Because it has never been able to learn something new except, hey, this is an identical copy of myself. But you want to have a specialization. This is why you have multiple AI systems or multiple agents. It is not that you just say, hey, you are a copy and just the task is different. No, you have to learn this in a configuration of multiple agents. You have to understand the multi-agent dynamics, MAS systems. So they co-evolve. Now the beauty is that the information agent that has not a world model learns to speak in a particular language, in a particular complexity, in a particular linguistic form, while the real agent that does here the job, that acts here in the environment, at first just listens here to the task-specific instruction by its bigger brother. So now we have something beautiful. We don't start at scratch, at zero with the control agent. The control agent gets a lot of very particular task-specific instruction from its bigger brother. And it tells it exactly what is the environment, what are you doing, but on a complexity level that this agent now understands. So they, if you want, develop a new communication protocol. Now, how do you have this joint pre-training? And the beautiful idea of this team here from Carl is they define now a loss function, a very specific loss function, and they call it a causal influence loss function. And we have a look at this loss function in 2 minutes' time. This is a critical mechanism that solves now the reassembly problem of different complexity sheets, hyperplanes. Because it acts also now as a language teacher between these two agents. In our simplest case, go to N and you understand what we have here. And this language teacher now forces the communication protocol between the agent not just to be accurate from the perspective of one agent, but also be useful from the perspective of the second agent, of the action agent in this defined world model. And of course, you have a feedback loop at every time element. Yeah? So the information agent has learned together in the pre-training with the other agent to build a world model and predict its temporal dynamics. So understanding now that the other agent was tasked with a particular job to do, the AI analyzes the situation and sends out a message to the control agent. Describe everything. Listen, you're in a room. Careful, in front of you, you have this. So you have to move here around over there, and then you have to do the action to open the fridge and take out the milk bottle and get it. And the action, the control agent listens now, understands, has a lot of information and acts now. So its action policy pi theta shifts now based on this message information. And then you have two questions that are necessary to understand the loss function. You ask, was this advice influential? So did the message cause a big change in the behavior of the active agents? And was the advice any good? So did this change in the behavior lead to a long-term stable outcome? And if you combine this into a mathematical formula, then you have a great causal influence loss function. And this is, I think, a real clever solution. You can see this here from a teacher-student perspective. But if you want, in my linguistic interpretation, what is this causal influence loss function in a language? It tells the information agent to follow this story at every step. So we tell the first agent, hey, your mission is to find a message that will significantly change what the control agent is about to do. But you will only be rewarded for this change if it turns out to be a genuinely long-term good idea with a high utility, as judged by both the agent's immediate confidence and the actual long-term rewards. Go invent a language that achieves this communication after you learned a world model. Do you see the different layers of complexity we are suddenly handling? So how can you implement this? And the authors have a beautiful format. I just make you a screenshot because they explain it in a beautiful way. So you have your loss function, and your loss function has 3 separate terms. Why? Well, it combines here the objective for the world dynamics modeling, the temporal dynamic of the room, the first one. Then you have to have a message consistency, a temporal coherence, and this is the second term. And then for the communication efficacy, we have here the causal influence loss function. So the first one is simple, no? If you want dynamics awareness loss, this objective grounds the information agent representation by training it to predict the consequences of the control agent actions. The temporal coherent loss is also rather easy. To promote the temporal coherence in communication, the information agent is also trained to predict the next message based on the current message through a specific prediction head you add to the transformer layer, no? With a particular loss function, this one. But now to the real interesting part. Oops, the arrow should not jump through the text, sorry. This causal influence loss function. So they built something they call an instantaneous causal effect, ICE. Defined now as a reverse Kullback-Leibler divergence between the control agent policy with and without this particular message from the bigger product. Great. Then they say, we build now a two-component utility function. This utility signal combines now two sources, no? Provides a low variance estimate of the long-term empirical advantage of taking an action. And the second source is the immediate change in the control agent's own value estimation. Typical PPO structure. If you go with GRPO, you have to be inventive to have here the group relative normalization. And then they say, on the third step is here, we normalize those signals. Ne? Combine, clipped to the final positive utility signal. So therefore, the final loss term maximizes the utility-weighted Kullback-Leibler divergence over all the trajectory taus from the joint policy that we define here. This is something beautiful. So this is, if you want, a mathematical notation of the loss function, how you have this pre-training of both systems. Real nice. But you noticed there's no condition that we tell the systems, hey, you have to use in your inter-agent communication, and maybe you only have a small communication bandwidth, that you have to use the human language. You can use any simplified, abstracted language. This is another fascinating, deep layer here of this new framework. And you know what? It tackles here my problem from the beginning of the video, from my last video, where I showed you the problem we have, the decomposition and the reassembly of different complexity objects where GPT-5 fails in their reasoning. And the key insight from this new framework could be that the language between the two agents for the reassembling of the pieces now should not be predefined or hand-designed by the human coder, but it should emerge, this is an optimization problem from two agents, as a learned protocol that is specific to the world model understanding of the information agent and specific to the set of agents that the control agent will do. So this language is now a learned protocol shaped now by an objective function that explicitly rewards an effective and a useful communication. And the second one, we have the interlink to the control agent. Now, if we go beyond the paper, this is now my idea. This is, if you want, I start to think about this in a different level. We have here the genesis of a new AI, agent-to-agent communication protocol, or let's call it a language. The genesis of a language of AI, and we face challenges. And we have the problem, are we sure that this communication has really some meaning to the real world? Let's have a look at this. So let's talk about the genesis of a language. This is nice. Imagine two agents, and you know this from philosophy or history or logic or signal theory. You have a sender and a receiver. The sender is shown one of several possible objects, a red square, a blue circle, whatever. But it cannot interact with these objects. Its only job is to send a message, a simple number, through a limited communication channel. Now, on the other hand, you have the receiver. The receiver cannot see those objects. It can only see the messages sent by the sender. Now, based on this message, it must now take an action. And you see exactly here are our two agents. Now it must take an action, so a control agent, like pointing now to a red square or pointing to a blue circle or whatever on its own board. So if the receiver points to the correct objects, we assume the communication process has been successful. If you want, primarily language has been developed, and both agents receive now a reward in the specific reward function of, let's say, +1. And if they're wrong, well, they get 0. Easiest reinforcement learning methodology. Now, at the beginning of the system, they have nothing. No? They have no idea, no shared language. It's absolutely 0. So the sender sends a random message and the receiver takes a random action. Nothing is happening. But you know, if you have thousands and thousands of run, just by probability, just by statistics, for one time you will be successful. By sheer luck. Call it luck. And suddenly you have a reward. And now we start with the reinforcement learning with our reward function, intrinsic, extrinsic functions. And if you go another 1,000 of rounds of trial and error using your reinforcement learning, you will see the emergence of a new communication protocol that has not anything to do with a human language. It is a communication between two AI agents. A more simpler example, no? The sender might notice that when it happens to send here the number 2, and the receiver happens to pick up the blue circle in this case, they both get a reward. So they do have a separated learning impression, but you know what? Given here the particular loss function, it is combined. So the sender now starts sending 2 more often when it sees the blue circle, and guess what? The same happens for the receiver. So they both now eventually converge on a shared arbitrary mapping of symbols that are now hopefully grounded here in reality. So whenever they send a 2, the blue circle seems to be the solution. So this is now their language, their new arbitrary mapping between abstract objects or symbols. So they invented a rudimentary language that is specific to the task. And this, if you want, is the emergence of something, of a communication protocol in its purest form, not of intelligence. Now we face challenges with this emergent communication, and you know them. You have the babbling equilibrium. No? If it's not really that, you know, they're just talking something, no? They just, maybe the guide says, hey, always the same message. Go north if you are in a puzzle, in a labyrinth. And the other one, the other worker, if you want here, learns to ignore this message and just does its own thing. Yeah? So somehow they might have some statistical nonsense. And whatever they reassemble now in their knowledge is a dysfunctional, non-communicative system. They are just babbling along without any meaning. Now the grounding problem is another problem. How do symbols, how do those messages, how do these communication elements are connected to the real world? Why is it to a blue circle? How we ground this? Because it could be, if you have a message encodes only a location, or maybe the color, or maybe the color of a particular object, you know, how you find this. So for the communication to be effective between the two agents, the symbols must be grounded in the aspects or the polarization or the interpretation, no, the representation of the world model that represents reality. And that is this representation relevant to the task of the control agent. So nice how many layers interact suddenly. And then we have the problem of meaning. If we ground it on reality, what does it mean? So overcome here the babbling equilibrium and solving here the grounding problems. You know, we have shared rewards, we have an information bottleneck solution, but the third solution is interesting. This is the approach by Carl. This is the asymmetric roles in the intrinsic objective with this particular loss function I already showed you. Because what we tell it, this information agent, your goal is to invent now a language that is maximally influential and useful to your operative part, to the other agent, the control agent. So this brilliantly, I would call it, it sidesteps the reassembly problem I faced in my last video with GPT-5. why GPT-5 fails. And here now we have a different perspective. We say, listen, the information agent that built a new world model for a particular action agent is not just rewarded for its own understanding of the world, but it is rewarded for making that understanding accessible and actionable for other agents in a multi-agent system. This now has a complete different learning dynamics and a complete different loss function and a complete different code implementation. And you know what we do here? We frame now suddenly a successful communication as a form of teaching where one AI agent teaches another AI agent the conditions of the environment it is in, it is acting within, and let's say had even some advice, hey, be cautious, right in front of you is a table on your way to the, refrigerator, so you have to walk around the table. If I think about here, vector space, I'm here in Vienna, and I immediately think here, given my education here, framing communication as a form of teaching is, if you want, a philosophical position, and this was represented by Ludwig Wittgenstein. And you see him here, 1929. Yeah, he was born in Vienna into one of the richest families here in Europe. He was in World War I and World War II. 3 of his 4 elder brothers committed suicide. And he was working on philosophy of mathematics and philosophy of language. And you know what? More than 100 years ago, he came to the same conclusion. Because Wittgenstein argued that words get their meaning not from what they refer to, but from how they are used within a shared activity or form of active life. So learning a language is not about memorizing its definition. It's about being trained to participate in these games, in this world model, in this representation, what we as humans think is the world around us and how we can interact with it. Interesting. But it's also about Heidegger, no? Let's talk about Europe. So, understanding the new layers of this new choral framework, I would argue the following. Heidegger's philosophy explains here the new AI agent's learning process because it is not unfamiliar to what humans are doing and doing for hundreds of years, showing how understanding emerges not from an abstract representation of the world, but from a skilled, embedded activity in the world. And I know from my friends in the US, I try to find someone in the US, maybe it is Robert Brandom, as a neo-pragmatism here, and he's also talking about here the same, no? He argues that to grasp a concept is not to have a mental picture, a world model of it, but to know how to use it in a game of giving and asking for reasoning. So a concept's meaning is its inferential role, what you can infer from in it, what it can be inferred from, and what actions you can take. So you see what? Those ideas, hundreds of years old, from the human, let's say call it philosophy, I'm faced currently now reading the latest AI research paper, and I think, hey, wait a minute, this is the same that I encountered here in my gymnasium times here, 100 years ago. And I say, how is this possible that I suddenly have the same ideas that how humans make sense of their own world? I encounter now trying to understand here the latest AI research papers. So those frameworks like Coral now, this new idea, provide here really a concrete, testable instantiation of those ideas, no? And it is, allow me to say, suggesting that both for the humans and for the AI systems, a meaningful intelligence is not about building a perfect mirror of the world as a passive observer only, but about learning to act skillfully and cooperatively within this world. So it is not about what you know as an AI system, but about what you can do in this constructed world model. I hope you like this kind of video. Sometimes I'm amazed by the sorts that you can find in a technical paper. Suddenly you're reconnected to philosophy. But hey, yeah, why not? See you in my next one.